So it's my honor to talk to you about density estimation and anomaly detection. I'm not 100% sure that's in focus. I guess it's in focus. So the plan for this hour is definitions and motivations. Why would we be doing density estimation, and what would we use it for? And then I will review some of the main techniques for doing density estimation, including sort of traditional methods, and then also a review of some of the recent things. We can also make these slides available someplace, so you can all have a copy. And just as everything else in machine learning is changing as a result of deep learning, I'll also talk a little bit about a very new technique that was published at NIPS in December called masked autoregressive flow, that is a kind of neural network density estimation. Then, after talking about density estimations and probabilities, we will return to the question of anomaly detection and ask, do we really need to estimate densities to do anomaly detection? Maybe there are some easier things we can do. So that's the plan. Okay, so what is density estimation? Let's assume we're given a data set of n data points. Each data point is a vector, say, of real valued features. And we'll just assume that they live in d-dimensional real space. Now, we assume the data all come from the same distribution. So, right, where I'm going to say that they're independent and identically distributed samples from some unknown probability density. So each x of I was sampled according to this probability distribution p of x of I. And our goal is to estimate p. And some of the requirements for p, of course, is that it has to always be positive throughout its entire range, or 0, it can't be negative, and that it needs to integrate to 1. And most of the time, there's always a distinction between a probability density and a probability. Right? A probability is always a number between 0 and 1, and it says, does a particular event occur? And you get probabilities by integrating the density over some region in the space of RD, because the probability of actually observing any single point it basically has, well, with some exceptions, has no probability. Well, why are we going to estimate densities? There are many, many reasons. Today I'm going to be talking mostly about anomaly detection because later today I'll present our work on the TAMO weather network, weather station network, where we're trying to detect failed sensors in a weather station. And of course, this is true for all IoT applications. I'd like to say the Internet of Things is the Internet of broken things, and we have to figure out which ones are broken. But I'll also talk, we can also use density estimation for classification. In fact, we could really use density estimation to do anything in machine learning. We don't because we don't have really good ways yet of doing density estimation in high dimensions. When the dimensionality is small, 1, 2, or 3, we have reasonably good methods. As the dimension of the data gets larger and larger, it gets harder and harder. We have to make more and more assumptions. Then the assumptions are not very accurate, and so on. But there is new excitement right now because of deep neural network density estimation may allow us to achieve this dream of being able to estimate densities in high dimension. And then we could really do anything using density estimation and maybe do it better. So let's look at anomaly detection. So there are many different definitions of anomaly detection. In our case, we want to think of there really being two sources of data. There's data that's the normal data. If we think about a weather station or our greenhouse sensors, the correct data readings will have some probability distribution, right? And then there's some different process, say the process that breaks the sensors, or we might be, there might be some other process, an adversary that's trying to attack our network, that would be generating the anomalies, the points from some that are generated by some different process. So for example, in fraud detection, the normal points would be legitimate financial transactions that would be perfectly fine. And the anomaly points would be fraud transactions. And of course, our adversaries want to make the frauds look as much like legitimate transactions as possible and still get money. So it can be quite a difficult thing. And in the sensor data case, our normal points are the correct data values, and the anomaly points are the bad values caused by broken sensors. So if we can estimate the minus log probability, so let's suppose that we have access to a large amount of normal data that's clean. And I should be careful. There's the normal distribution, of course, like the Gaussian distribution. I'm not referring to that here, although I will be using a lot of Gaussian distributions. So if I'm not clear about whether I'm talking about normal data as in the sense of not anomaly data, raise your hand and ask me a question. In fact, raise your hand and ask me a question anytime. So let's assume that we have a data set that is of our normal data. We have learned a probability density P of x, and then given a new point, like a query point, if we want to ask, well, what kind of a score should we assign as an anomaly score? One thing we can use from information theory is known as the surprise. Okay, and the surprise is the minus log probability. And this is a good name for it because if an event of probability 0 occurs, then minus log p is positive infinity. So we're infinitely surprised when something impossible occurs. And similarly, if something with probability 1 occurs, we have 0 surprise, right? Because the log of 1 is 0. So it makes a lot of sense. This is for probabilities, but I just said densities. But in our case, we're interested in the very low probability events, which are also the low density events. So it's okay to use minus log density as an anomaly score. So the idea would be to score points. So for example, I generated a bunch of data from a normal distribution. My nominal, sometimes I'll use the word nominal to be, but that will be the normal data. I generated nominal data from a standard normal distribution. And my anomalies I generated from a distribution whose mean is at 3, but has the same variance. And so I have 100 nominal points and 10 anomaly points. And what I've done over here is I've plotted this. You can't really read this very well, I see. This is the value of x. X just runs, of course, from minus infinity to plus infinity, but all the points are really concentrated here around 0, which is the mean. And the vertical axis is minus log probability, so it's the surprise. And so these red points are the points from my anomaly distribution, and the black points are from my nominal distribution. And what we see is that actually the point that got the highest surprise score was actually a nominal point. I mean, probability distributions often have tails, and so there will be outliers even in the normal distribution. So the first is if we sorted them in order of decreasing surprise, our first two would be false alarms. Then we would get a couple of true alarms, then maybe a false alarm, then another false alarm, then a bunch more true alarms, and so on. And we could set a threshold, which turns out in this case to be 2.39. That's the anomaly score of that red point there. That would give us 100% detection or recall on the anomalies, but we would have 8 false alarms. So just as in supervised learning and classification, where we think about false positives, false negatives, and so on, here we think about false alarms and true alarms, and we always face a trade-off between them. If we set the threshold too high, we'll miss some of the true alarms. If we set it too low, we will miss, what did I say? Yeah, we'll have a lot of extra work to check all of the false alarms and realize that they were false. So any questions on that so far? Okay, well, if we have if we have density estimation, another thing we can do is classification. And to do that, we set up a conditional model. So how many of you are familiar with the notation of probabilistic graphical models? This is one thing okay, so I will try to explain it a bit. But so the idea of a probabilistic graphical model, this is a good one to begin with, is we imagine we have some random variables, and we'll create a node for each random variable. And this node here is a node for the random variable y, which might be our class label. So let's now think we're in some supervised learning case and say we're doing optical character recognition. So the famous MNIST data set, we imagine that then y is the true identity of a digit, and x is going to be an image. So x is actually a matrix or an array of pixels, but we can treat it in this notation as just a variable. And this arrow indicates that there's a probabilistic relationship between the value of y and the value of x. In particular, we often think of a probability model as a theory of how the data is generated. So in this case, our theory of how the data is generated is first a person says, I'm going to draw a 2. So they make that decision. So they choose a value for y. And they choose it from some probability distribution. Maybe it's all digits are equally likely. I think usually in financial things, all digits aren't equally likely. Then 9s are less common than 1s and 0s. I don't remember. But in any case, there's some probability distribution for how I choose which digits I'm going to draw. And then based on that, I actually draw the 2. I create this image by putting ink onto the paper or onto my phone or whatever. So as a probabilistic modeler, we have to choose probability distributions for these things. So we might choose that the probability distribution for the digit y is a discrete distribution, that is a multinomial distribution that assigns a probability to each of the 10 possibilities. And then x is distributed according to this conditional probability distribution. So right, this is the probability of drawing that image of a 2 conditioned on that I want to draw a 2. So that would be much higher than if I wanted to draw a 4 and I drew that 2. That should have very low probability, right? I should only draw 2s if I want them. But sometimes a drawing can be ambiguous, right? Many 7s and 1s look rather similar. And so those probability distributions maybe have some overlap. So this is known as a conditional density estimate because this is a conditional probability, right? Given that I have chosen a value of y, then what value of x should I generate? So you can also think of this as really a shorthand for 10 different probability distributions, one for each digit. So that's why I've written here, I'm going to make a very crude assumption that the pixels have a normal distribution with some mean that depends on the value of y. So there's some mean vector mu of y. And in this case, right, the mean would actually be an image with some pixels in it, with some ink on them. It would sort of be the ideal 2. And then the variance, this is the covariance matrix, so it describes how all the various pixels are correlated, and that would describe how 2s vary. It would be quite a poor model, although I note that there is, I think, a paper coming out in Archive later today where they look at Gaussian distributions for images and find that actually they're not so bad if you use mixtures. So anyway, so if we could do, the reason we don't usually do this is that we have so much difficulty modeling this conditional distribution. But if we could do it, then to make our classification decision, of course, we have to run this thing backwards, right? The thing we observe at classification time is we observe the image, and now we want to reason backwards and figure out, well, what is the probability that the person was trying to draw a 2 versus a 4, right? And so we can apply Bayes' rule to calculate this, right? So the probability of y given x, which is the reverse direction, is the background or prior probability of y times the likelihood of x given y. So this says how likely is it that the user was trying to draw a 2 and drew this image. And then we have to normalize it so that the probability is summed to 1, which is all that the denominator is doing. So we can think of this as saying which class label y best explains the observed image. And as I say, the challenge is usually that this generative model of the x is very difficult to model. And so, but you may have seen this kind of model called naive Bayes, because this is often called a Bayesian classifier. Well, it would be naive if the covariance matrix here was just the identity matrix. That is, each pixel in the image was generated independently of all the other pixels, assuming we're trying to draw a 2. And that's what makes naive Bayes naive. If you use a more complex distribution, it just becomes a Bayesian classifier. It's no longer naive. And it's called a Bayesian classifier not because we're using Bayesian statistics, but because we're just using Bayes' rule. So it really should be called, I don't know, a probabilistic inference classifier, because we're doing probabilistic inference. Okay, so those are two of the motivations. But really, you know, if we can estimate probability densities for all of the complex things in the world, then we can have I think, much better probabilistic, much better machine learning. And so I'm one of the sort of believers in the probabilistic religion of machine learning, although the reality is that we don't have ways of dealing with high dimensional probability distributions, and that's why we instead use more discriminative type learning algorithms, function learning algorithms, like our deep nets, support vector machines, things like that. Okay, well, suppose we want to estimate a probability density. How should we do it? Here are four basic approaches. So I guess I'm repeating myself. The first one is to assume that our data come from some known parametric probability distribution. So if we assume that our data are normally distributed, or Gaussian distributed, then this is their probability density. Right, and the basic idea is that we're going to take, this is for the vector valued case. So x is a vector valued random variable, or it could be an image valued random variable. And we ask how far is x away from its average or mean value, and that's a vector subtraction, right? We take its transpose and multiply it by the inverse covariance matrix, and then again multiply it by this. And so this is kind of we can think of the inverse covariance matrix as kind of squeezing and rotating the distances, kind of like a distance metric that takes these basic differences and rotates and normalizes them appropriately, rescales them. And all this mess up in front with the determinant of sigma and 2 pi to the d, that's just to make sure that this integrates to 1. And I always have to look it up on Wikipedia. I hope I got it right here, but that's the... so now, if we assume this distribution, then how can we fit it to data? Oops, I forgot, I saw this error last night. So what we can do is there should be a sum, maybe I'll just fix it right here. This should say the sum over I of x of I. Yeah, okay. We just take the average of all the data points. So it's vector sums, and then we're just taking an average, and we get our estimate for the mean of this distribution. And then estimating the covariance matrix is more complicated. We have to take subtract the estimated mean, mu hat, off of each of our data points. That's called centering the data. And then we take the outer product. So this is the opposite of the inner product. It's the outer product. The product of these two vectors will actually give us the matrix. We add up all those matrices and take their average value, and that's the covariance matrix. So super easy, right? We don't need a TensorFlow and fancy things. This can be done just in a couple of lines in any programming language. So here's an example. I generated 100 data points from a 2-dimensional Gaussian in which the mean was 2, 2. So the mean point of this distribution is somewhere there. And the covariance matrix has this structure. So what this says is basically the first dimension, x1, has a variance of 1. If we just projected this down onto this axis, right, it would have a distribution like this that would have a variance of 1. And this axis has a variance of 4. So if we projected this over here, it's a much more spread out distribution, right? But they're also not independent. There's a diagonal structure to it, and that's because I've set these covariance values to be non-zero. So that makes it kind of an ellipsoidal or elliptical kind of distribution. So now if I do what I showed on the previous slide, estimate the mean from these 100 points, it's not quite 2 by 2, but it's close. And the covariance matrix, we get the diagonal elements right, because that's pretty easy. The covariances, you'll notice it's always a symmetric matrix. In fact, it's also known to be what's called positive definite. So the estimates are pretty close. I mean, it's only two-dimensional, should be close, but. Okay, so that's the first idea for doing density estimation, is assume the data came from some known distribution, and all we have to do is estimate the parameters of that distribution. So this is also known as parametric density estimation because we just have these two parameters, mu and sigma, and we need to just infer their values, and then we know the distribution. Of course, most data is not normally distributed. We have heavy tails because of strange phenomena. Maybe we have nonlinear relationships. So what do we do when that happens? We in the 1950s and 60s, they used normal distributions for everything. And really, I think one of the big contributions of modern statistics and machine learning has been to show how we can do nonlinear fitting to data. Well, one idea is to use what's called a mixture model. And this is quite similar to the probabilistic classifier I mentioned a moment ago, except that it's totally unsupervised. So we're going to assume that the data come from some number of what we call them mixture components, or sometimes people call them clusters. And I didn't put the number here, but let's say it's capital K, I guess. So maybe 2 components, 10 components, 50 components. And each component has some probability of being selected. So again, this is our variable C. So to generate a data point, we first say, well, which component are we going to generate the point from? And that's P of C. And then, having chosen that, then we generate the point according to probability of X given C. And so it has the same shape to it. But it's important to realize that it's fully unsupervised. All we observe is the X's. We never get to find out what cluster things belong to. That's a part of our model. So in a mixture model, it's still in some sense a parametric model. We have to choose the number of clusters K. If we fix that, then technically speaking, it's a parametric model, because parametric models always have a number of parameters of fixed dimensionality. So each mixture component then has its own conditional density. So just again as an example, suppose I created a probability distribution that consisted of drawing samples from these two Gaussians. This is the same one I used before, and here's another one with a different covariance matrix. And I set it up so that the probability of generating a point from cluster 1 is 2/3, and the probability of generating it from cluster 2 is 1/3. And then the cluster 1 points are the circles, and the cluster 2 points are the little pluses. But of course, when we get the data, we don't know which ones are the pluses and which ones are the circles. It's just a bunch of points, and it has a kind of sort of a U-shaped or banana-shaped distribution. That's non-Gaussian, right? So the reason we want to use a mixture model is to accommodate that banana shape in this case. Well, fitting mixture models is much more complicated because we have to, if we knew, if we knew which ones were the pluses and which ones were the circles, then it'd be easy, right? I mean, we could count up the number of pluses and count up the number of circles and figure out it's 2/3, 1/3. And then we could just separately take the circles and estimate the mu and sigma for cluster 1, take the pluses, estimate the mu and sigma for cluster 2. So the trick to fitting a mixture model is to try to assign values of C to each data point. If we knew, so we're going to sort of guess which cluster each data point belongs to, and then fit our models of those clusters. And the general strategy is to do that repeatedly. So we're going to start by randomly assigning the points to clusters, and then we'll fit a model for each cluster. And then we'll ask for each data point, which cluster do you fit better? And we'll reassign the points to the clusters, and then re-estimate the clusters and so on. So let's go through that more mathematically. So we have to choose the number of mixture components, and then we'll create a matrix R that's kind of an auxiliary data structure for us. I call it R for responsibility, because we want to know which data point is, which cluster is responsible for each data point. And we're going to allow probabilistic responsibility. So if we have a data point, if we had a data point right here, it could have come from cluster 1 or it could have come from cluster 2, right? Maybe with equal probability. So the responsibility for that point might be 0.5, 0.5. Whereas this point out here, the responsibility is going to be something like 0, 1. And similarly, this point out here, even though it's very unlikely to have come from either of the clusters, it's more likely to have come from cluster 1. So it might still have a responsibility very high for cluster 1. Okay, so we randomly initialize. So the idea of R sub ki is that it is the probability that data point xi was drawn from cluster k, right? Probability that C sub I was equal to k given x sub I. And this is called the membership probability or the responsibility. Okay. So we can randomly initialize these things. It's important that they always be non-zero, and therefore non-1 also, right? 0 and 1 have such special power in probability. And we just have to make sure that they do sum to 1. And then we do this main loop, and this is called the EM algorithm, or the expectation maximization algorithm. And probably was one of the coolest things that was discovered. I think it was only published in 1984 or something, so it's relatively recent. At least I consider anything that was done after I was born to be recent. You know, it's like most things in math, right, were done by Gauss or Newton or something, and here's something that was discovered just a relatively few years ago. It seemed much more recent when I was a graduate student, because it was about the time that I was a graduate student that the paper came out. So the idea is we alternate between an M step and an E step, and so that's why it's the EM algorithm. Maybe it should have been the ME algorithm, but yeah. So in the M step, we assume that we have the right responsibilities, that those responsibilities are correct, and then we can estimate the parameters of each of the Gaussian distributions. So we can say, well, our estimate for the probability basically the probability of generating a point from cluster K, we just add up all the probabilities of the responsibilities for cluster K and normalize them. And similarly, we can estimate the mean of each distribution as the weighted average of the points weighted by their responsibilities. So the mean for class K is the probability that the point belonged to class K, and then we have to normalize by the probability of drawing any point from class K and N. And the same thing for the covariance matrix. Again, we're taking the outer product, XX transpose, of each data point, but then weighting it by the probability it belongs to class K, or cluster K, component K. So having done that, then we can re-estimate the responsibilities. So we can set the responsibility for data point I, being cluster K, to be the probability of drawing a point from cluster K times then the probability of generating point xi from that cluster. But then we go through and normalize those so that they sum to 1. We have to make sure that's true, because as we saw, some points have a very low probability of being generated by any cluster, but we still force the responsibilities to sum to 1. So you can do this, alternate these two steps until convergence. It's important to realize that this is a local search algorithm. It turns out that we like to talk a lot about the shape of the likelihood function, or the shape of the objective function in our optimizations. And for a mixture model, there can be multiple peaks in the landscape. And we really want to find the highest peak that has the maximum, that's most likely to have generated the data. But this algorithm basically starts somewhere on some place in the landscape and climbs, trying to maximize the likelihood until it reaches the top of a hill. That hill might not be anywhere. I mean, here, if we climbed this hill, we would not end up on Mount Kenya, which is maybe the global maximum for the country. Is that right? Yeah. So to use this, you often need to randomly try different starting points and keep the one that gets you to the highest peak. And you can imagine, I mean, even here, how many random starting points in Kenya would it take before you got one that got you so that you were on Mount Kenya as opposed to something else? Can be. So it's a local search algorithm because it's just climbing uphill. So I ran, I'm more of an R programmer than a a Python programmer. So I did this in R, but in R there's a package called mclust for model-based clustering. And here's what the fitted model looks like. So this gives you a sense of, the banana-shaped distribution. It does a pretty good job of finding it. I've put the pluses in the circles again just for our eyes because it never knew that. It didn't know which points belong to which distribution. And in fact, if you dig into the fitted model and look at the responsibilities, they're not all correct. We can see that the true values, right, for the probabilities P of C, those are also known as the mixing proportions. Because we call this a mixture model because it is, right, I mean, if we think about it here, each of these is a model, and then we are taking a mixture of them, right? We basically roll a dice, P of C, to figure out which model we use to draw each data point. So it's a mixture model. So these are called the mixing proportions or the mixing probabilities. And how well did we estimate them? Well, it said the mixing proportions were 0.649, 0.351, so pretty close. And then the mean of the first distribution was 2.2, and it got it at 2.0 and 1.96, so it did really well for the circles. Of course, it had 100, there are basically 100 points for that one. Didn't do this one so well, so the second, it's got the mean at minus 0.6, and it should have been minus 1. So it doesn't always find exactly the right means. What's interesting is, we sometimes ask two kind of theoretical questions in statistics. One is what's called the convergence and probability, which is the idea that if we had enough data, as the amount of data went to infinity, would we find the true values of all these parameters? And the other is convergence in distribution, which says, as the amount of data grows, do we just find the right combined distribution? And one of the things about mixture models is often we might have too many components than reality, but we can often still get the right distribution. And so in particular, I don't think we're going to discuss topic models here, but there are a lot of, high-tech probabilistic mixture models, like topic models, Dirichlet process mixture models in general, where it automatically considers many different sizes, many different values of k for the mixture. And it's known that those are not consistent algorithms in the sense they don't converge. There's no sense in which it even is a sensible question to ask, do they converge to the true parameter values? But they do converge to the true distribution. And so if we're just doing density estimation, we only care about that true distribution. So mixture model summary, so one thing is that with enough mixture components, you can fit virtually anything. Yes?
I want to suggest also, when you use the example of trying to find the global maxima of
yes, in Kenya.
And it's just 2D. And
yes.
You were mentioning earlier on, maybe you'll get back to this, about problems of more dimensions.
Right, like 8 gigapixel camera, and we have 8 billion parameters, yes.
It took me a long time to get my head around visualizing high dimensions, not visualizing them, but realizing how much of a different beast
yes.
Maybe that's worth just emphasizing.
It's a very good point that our intuitions in 1 dimension, 2 dimensions, 3 dimensions do not extend to 100 dimensions, 1,000 dimensions, 1,000,000 dimensions. One thing that doesn't extend is that all data points are extremely far apart in high dimensional space. But one reason to hope is that maybe often we have these very high dimensional data like images, but we really think that the image probably can be described with many fewer parameters than the number of pixels, right? We know we can, we know the telephone makers and the camera makers have been having this arms race, 8 gigapixels, 16 gigapixels, 30 gigapixels, but the information in the image is still basically the same. I don't know, unless at some point you're trying to count like the number of hairs in my beard or something. But for the things we care about, we don't need more pixels. So there's also this question of task-relevant information. Yeah. But maybe if there's a lower dimensional distribution, I thought about putting in here these latent variable models, but sometimes we can estimate the probability density in a lower dimensional space that we think has all the important sources of variation in it. Anyway, let's see. I mentioned, so with a mixture model, in theory, we can fit almost any arbitrarily complex distribution, in theory. In practice, getting EM to work would be challenging. The EM algorithm is a local search algorithm. In the last few years, there have been some very interesting so-called spectral methods that are based on doing calculating eigenvalues and eigenvectors and actually components of higher dimensional tensors. And with those methods, particularly I think of Anima Anandkumar at Caltech. She's probably the goddess of these methods. She can guarantee to find the global optimum. So there are these new techniques. They're statistically not as efficient as EM, but on the other hand, they get the right answer, so that's a good thing. There's been a lot of research in the last 5 years, 10 years in how to fit these mixture models more reliably. And the other thing that's hard is choosing the number of mixture components. And a lot of packages, they will have heuristic techniques for doing that are actually quite good. Okay, so we've talked about parametric model where we assume we know exactly the distribution except for some parameter values. Then we had a mixture model where we're still kind of parametric except for the value of the number of mixture components is free, and we could choose that. Now we go fully non-parametric, and we imagine taking the limit where we're going to have one mixture component for every data point. Okay, and that's the idea of a kernel density estimator. So we define a mixture model with one component for each data point. So the probability density for x is we imagine putting something we call a kernel, which we look at the distance of x from x to one of our data points, and this is in some appropriate distance measure with some parameter sigma squared. Just add those up and normalize them, because so for instance, we usually use the Gaussian kernel. So this is the one-dimensional version of the Gaussian distribution, right? And we know that it sums to 1, and so if we take n of them and sum them, they would also sum to 1 if we divide by n. So it's probably easier to see this in a picture. So imagine that we had these data points that are these black bars here. We put a Gaussian distribution whose mean is centered on that bar, and another one for this one and this one and so on. So we have 1, 2, 3, 4, 5, 6 mixture components. And then to ask, well, what's the probability right here, right? We just add up all these red curves and divide by n, and that gives us this here. So this is what our estimated probability density looks like. So it's very cool, but it only works if we use a very simple functions here, right? Because if we had a full covariance matrix for each of these, we would have many more parameters than we have data points, and that wouldn't work. So generally, we only fit one parameter, which is how wide these kernels are, how wide these Gaussians are. And again, there's a huge literature on how to do that automatically, and there are some techniques for letting the size of the kernels vary around in the space. And maybe we'll even hear a little bit about that. I don't know. So the choice of kernel, it turns out, is not hugely important. Some people just use like a little triangle kernel. You can use a square box kernel, and you can also get very fancy with fancy kernels. But the theory tells us that that's not too important as long as it's a local kernel. But the choice of bandwidth, that is how wide the kernel is, that's super important, right? If I set the kernel too narrow, then I get a bunch of very spiky distribution where you can sort of see each of the original data points becomes one of these little spikes. If I set the kernel too wide, I get this big smooth thing. It just starts to look like a big Gaussian. And so somewhere in between is probably the right kernel width. And so again, there are in most packages there are ways of automatically choosing this, or you can use independent validation set, right? So a typical thing in any of these design decisions, including the number of mixture components k, is you have your data randomly divided into two parts, maybe 50-50, maybe 70-30. and then fit your model to the one part, and then calculate what the holdout likelihood, so calculate the log likelihood on the held out part. So that would be the log of the probability of each of the data points in your validation set or your holdout set. And you want to make your parameter choices to maximize the probability of the held out data points. So even though it's unsupervised learning, you can still use holdout or cross-validation strategies to set parameters. And I'm using words like holdout and cross-validation without knowing whether you all are familiar with them. So who knows about cross-validation? Okay, so small amounts. Okay, well, holdout is just what the word says. We're going to hold out some part of our data and not use it to estimate the model parameters. Instead, we're going to use it to check how well we're doing. And this is a very important principle in machine learning, that if you use the same data to fit the model as to evaluate it, it's like knowing the answers to the test before you take it. So you really need to have your training data and then your separate validation data. And it's also true that if you use that validation data too many times, it just becomes training data. So, and so sometimes we even have multiple holdouts and have our training data and then sort of holdout 1, holdout 2, holdout 3, and we use them to make different decisions or to estimate different quantities. Anyway, you can use holdout methods here. Cross-validation, the simplest version of it is that we divide our data in half and we fit the model twice. We fit it to data set A and then check how well we did on data set B. And we fit it to B and use A to check how well we did it. And that's the idea of cross-validation, is we use A for B and B for A, so we're sort of crossing over. And you can do it so-called tenfold, where you divide the data into 10 parts and then fit the model 10 times, each time fitting it to 9 out of those 10 parts and using the one remaining part to check how well you're doing. And in the limit of the sort of infinite computer time, you can divide the data set into each individual point and just leave out one data point at a time, and that's called leave one out cross-validation. So here we could use, I would say, divide the data in half and use half of the data to fit the kernel density estimates, and use the other half to measure how well we're doing in terms of how well we fit the data. Okay, well, challenges of kernel density estimation. I mean, kernel density estimation is super cool. It can really, again, it can fit any distribution very well. But it doesn't work well in high dimensions. In high dimensions, it suffers from what's often called the curse of dimensionality, which is to say that it turns out the amount of data that you need to achieve a desired level of accuracy grows exponentially with the dimension. So it grows as e to the power d plus 4 over 2, or basically e to the d over 2. If we we would need exponentially more data as the dimensionality goes up. So doing a one-dimensional or two-dimensional density estimate is pretty easy, but if we did 100 dimensions, we would have e to the 100th power, well, e to the 50th power here amount of data. It would be huge, right? So this is the main reason the kernel density estimation is mostly reserved for very low-dimensional problems. But of course, there are people working on fixing that too. Now we're going to take a little bit of a detour on our way to using a neural network density estimator. And I don't know what time it is. How am I doing? Okay, well, I'm going slower than I did in practice, but
I think it's fine.
okay.
That's yesterday we underran.
Yes. As long as we get to lunch on time, right? So let's suppose that we have these d-dimensional vector of random variables, and we want we have data set, many x values for in our data set, and we want to model the joint probability distribution of these points, what we've been trying to do all day today. Well, one thing we can do is in probability, there's something called the chain rule of probability that says any joint distribution, p of x, we can factor into a product of conditional distributions. So we can have a distribution P of x1 times a distribution P of x2 given x1 times P of x3 given x1 and x2, dot, 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 all the way up to times P of the last xd given all of the others that we've generated before. And so this, if we drew this as a graphical model, we'd have x1, x2, x3 as a long chain of arrows. But each point would be able to look at all of the previously generated values. And so we could model the probability density of x1 by using a kernel density estimator maybe, and then we can model each of these conditional distributions using, say, regression methods, and eventually using neural networks. So let's see what this looks like. How many of you are familiar with linear regression for fitting a set of points? Okay, so, right. So almost all of us have seen linear regression in the statistics class. Linear regression is let's set it up. So let's assume we have capital J input predictor variables, and we're trying to predict a response variable y. So maybe we're trying to, I don't know, what would be a good thing? I don't know. A very simple thing would be to predict height from weight. So if we observe someone's weight, can we predict how tall they are? And standard least squares linear regression models calculate a conditional probability distribution that looks like this. The probability of y given x is assumed to be a normal distribution whose mean is some function of x and whose variance is a constant sigma squared. And the mean function is this linear function that we fit with linear regression, right? It's got some intercept term beta naught, beta 1 times x1, up to beta j times xj. So it's a simple linear function of the inputs. And sigma squared, which you often don't, when you run this in a linear regression package, they usually just show you these betas here, and they don't necessarily show you sigma squared. But this is the residual sum of squared error. So it is there. It's just not labeled as a parameter. So we could also do this with neural networks. So we could replace this mean function with some complicated neural network and train it to minimize the squared error, and it would be the same thing. But so the key thing is that the randomness is really this normal distribution around this predicted mean. So now let's, with that idea of breaking the whole problem down into a series of smaller problems, we can try to understand masked autoregressive flow. And this is by a guy named Papamakarios and collaborators from University of Edinburgh, published at NIPS this year. And so they apply the chain rule of probability. I'm going to write it this way, that our conditional probability of the jth variable is determined by all the previous variables x1 up to xj minus 1. And they say that's going to be modeled as a normal distribution whose mean is mu j and whose variance is the e to the alpha j squared. So this is a little bit weird, but we'll see why in a moment, where mu sub j is actually going to be some neural network that is a function of all these previous variables, and alpha j is going to be another neural network that's a function of all the previous variables. And the advantage of this particular formulation, right, is we need the variance to be positive. But it's hard to constrain a neural network to only output positive values. And so the idea is we let the neural network output any real value here, and then we exponentiate it, and it becomes positive, and we square it because it's a variance. And so we'll see that that's convenient. So we're assuming each one of those little conditional distributions is really a regression model that assumes that the errors or the randomness around the mean has a Gaussian distribution. There's a little trick that we're going to use called the reparameterization trick. Suppose we wanted to sample xj from this conditional distribution, and it has this mean that's very complicated and this variance that's very complicated. An alternative is that we can sample a variable uj that's a standard normal from a standard normal distribution, and then we can take uj, multiply it by the standard deviation, which is e to the alpha, then add in the mean, offset it by the mean, and that will give us the value xj. So this is a standard technique for if you have a random number generator for standard normal Gaussians and you need a random number from this Gaussian, you just use this technique, right? You scale the random number and then shift it by the mean. But it turns out that's actually pretty handy because we can also view what we're doing here as a model that takes a vector of these standard normal Gaussian random values and transforms it to generate the vector x that we're trying to model. So, and it does this, of course, by sequentially first generating x1, then x2 given x1, x3 given x1 and x2, and so on. But we can just step back and think of it as a great big fat function f, and what it takes as input is a bunch of standard normal random variables. And so now, if we want to compute the probability density, p of x, we want to just calculate the inverse of this. So given x, we want to calculate f inverse of x. That should be a boldface x there. And we could almost just plug that into a standard Gaussian, j-dimensional Gaussian distribution and evaluate its density. So we can convert the problem of this density, probability density over this very complex input space into estimating a probability density using a standard normal distribution, which we know. I say almost because it doesn't quite work. What we have to do is multiply it by this thing here. And I could wave my hands. The intuition is this thing by itself might not integrate to 1, so it might not give you true density values. But we can rescale it by computing this, which is the Jacobian matrix. So this is a shorthand for calculating all the partial derivatives for each of the possible values of x, the output of f of x, with respect to the input. And then that gives you a big matrix, and then you take the determinant of that matrix, and then you take the absolute value of the determinant, and that turns out to be the magic number that scales this so that it becomes a probability density in the x space. So I don't know if I'm communicating how cool this is, but we can take so we have some possibly very complex distribution in, say, images or music or greenhouse sensor readings, and through a series of transformations, we can turn that into a standard Gaussian distribution, and then we can just look up its density there. And we do it by, like a lot of probabilistic things, it always involves running a model backwards. And so the trick here is to make a neural network that we can run in reverse. I wrote down this f inverse, but can we compute that? Can we actually invert a neural network? I should point out that if we could convert it, this complicated thing here just turns out to be summing all those alphas and taking e to the minus that. So it's actually very easy to compute. We like to do this because we like to show off that we remember what a determinant is and things like that. But it turns out this f function is easy to invert. So remember 3 slides ago, we reparameterized x, this as to be x being uj e to the alpha j plus mu j. We can just solve this for u in terms of x. And so that's the basic thing we do here. And so we can write uj is xj minus mu j e to the minus alpha j. And we can compute mu j from our neural network fj, and we can compute alpha j from our neural network gj. And so given x1, we can we'll plug that in trivially. Then x2, we subtract off mu2 e to the minus alpha 2, and we get u2. And so as we're inverting it, we're figuring out what would have been the u values that if we plug them in would have generated this x that we're looking at. And once we have those u values, we know the u values are supposed to be distributed as a multivariate Gaussian with 0 mean and a variance of 1. And so we can look it up. a little bit of a problem. I think the problem is it doesn't quite work, but one thing we want to do is we'd like to express this as a single neural network. I've described it as if we have all these different neural networks for FJ and GJ and stuff. But these guys thought, well, I want to run it on GPUs using TensorFlow. So what I'm going to do is, this is where the word masked comes in. So I should break up this thing. The algorithm is called masked autoregressive flow. A flow is this idea that we take the U's and they flow through and turn into the X. And it's a probabilistic flow if we make sure that the probability density integrates to 1. Autoregressive is a terrible name for applying the chain rule of probability to break it up into the individual, predicting each xj separately. And masking, the idea is that they set up this neural network so that if we're trying to calculate, say, fj right here, we want to make sure that it only depends on x1 up to xj minus 1. So we forced the neural network to only look at the weights that are contributing, that look at these inputs and contribute to this output. So there's a different mask for each output that makes the neural network kind of have an overall triangular structure, right? The very first values can only depend on x1, and then this one can depend on x1 and x2, and so on. And this last value down here can depend on all of x. So a lot of the weights, effectively we're setting a lot of the weights in the neural network to 0. And when you do this, then instead of having many, many different neural networks, we can just do it all with one neural network that calculates f and g. So here's an image from their paper. So they created this two-dimensional distribution. It's very non-Gaussian, kind of warped thing. You know, the ultra, I guess it's more like a spaceship or something. And if you fit a single mass autoregressive flow network, this is the fitted model, the fitted density, not so good. And if you look at the U values, so these are the U values, and since this is two-dimensional, there are only two U values, U1 and U2, and so we can plot them here, but then for each data point we get two U values. This definitely does not look, it should look like a circle, right? It should be a Gaussian bump with zero mean and unit variance. Instead, it has these weird sort of trailing things here. So this shows that the assumption that when we run the network backwards to calculate the U values, that those U values would have a joint standard Gaussian, that's wrong. So what they do is they stack maths on top of each other. So they now treat this as the data, and they try to build an MAF that will generate these U values from some other U values. And they do that in this case. If we do it 5 times, we end up with this as the fit. So now our fitted density is pretty good. It's got a few wiggles and wobbles. And our U values, 5 levels deep, do really have look like they come from a nice circular normal distribution. So, yes?
So that means they need a neural network for each of those layers as well? Is that right?
So we actually have 5 of these in this case stacked on top of each other. So it's now definitely a deep neural network.
It's a deep.
Yeah. If I understand it correctly. I know Papa Makarios is doing some sort of webcast today explaining this method. So another thing that's very cool about this is that a few months ago, Google announced this thing called TensorFlow distributions, which is a package for modeling complex probability distributions using the TensorFlow system. And this is one of the things that they do. So I have a student that's trying to get this to work now on image data for anomaly detection. And we'll see how it goes. So in their paper, they compare against several recent neural network methods, and they compare against just using a standard Gaussian distribution, a multivariate Gaussian distribution. And these are on various different data sets. And what we're reporting here is the negative log likelihood of the data. So maybe I should be explaining that a little bit, or actually the log likelihood. So let's yeah. Right. So the standard measure we use, right? We have learned a. Let's see where I can get myself a. Right. Suppose we have learned a probability density p of x, and this is our model. And then we have a bunch of data, right, x1 up to xn of data points. So how can we evaluate whether our probability model is good? Well, we say our probability model is good if it assigns high probability to the data. And so we could say that because the data points are independent, we could write this as the probability of x1 times the probability of x2 times the probability of xn. That's which is basically the probability that the model assigns to our training data. And you multiply probabilities to get the probability of x1 and x2. Because they're independent, we can multiply them. Or if we take logs, this becomes, right, the sum over I of log of p of xi. And this is known as the log likelihood. These are likelihoods, and these are the logs of the likelihoods. So this is the usual measure we evaluate. It's kind of fine. You might ask, well, what are its units? And its units are things called nats. So if we used log base 2, it would be bits. It would be the number of bits of information that are encoded by this probability distribution. And if you ever want to have some intellectual fun, you can go study information theory and learn all about these things. But let me switch back to my other thing. But the drawback is that there is, unlike when we're doing something like error rates, and we know that 90% correct means that 9 out of 10 of the points will get right. When we see a log likelihood like minus 0.02, we don't really know how to interpret that. We can only use it really as a relative measure, not as an absolute measure. Because ideally, we would assign infinite likelihood to each data point. So the main thing is to look vertically in each of these and ask, well, who had the highest value? In this case, there was MADE was the model that preceded the masked autoregressive flow. It's quite similar, but they used a mixture of Gaussians for the U values, and that did the best there. For this gas data set, it was a 10-layer masked autoregressive flow. For this is some sort of high energy physics thing. Again, it was this one. For mini boon, it was a 5-layer MAF. And for, I don't know what BSDS 300 is, it was a MAF, but they had to use a mixture of Gaussians to describe the U values to get enough flexibility. So it doesn't, it's not a silver bullet, but it's a very shiny one. Okay, well, let me now, my second part is much shorter. Let me talk about other anomaly detection approaches. So it's reasonable to ask, here we've been working really hard on getting the log likelihoods and modeling the densities correctly, but maybe for anomaly detection we don't really need to do that. Maybe there are simpler things we can do that would still work well. What do we really need? Well, we'd really like to make sure that we, for instance, that we rank all of the data points by how anomalous they are. Because we're going to go through them in rank order and examine them to see if they're fraudulent or if the sensor is broken or whatever. So we don't really need to know their true log likelihoods if we just get the order right. So that's one idea. Another one is maybe all we need to do is really just detect the points that are, if we've got some threshold, detect all the points that are less likely than that threshold. So maybe we don't need all this complicated machinery. And so there are some very simple algorithms that actually work pretty well. One of them is nearest neighbor anomaly detection. So let's assume we can measure the distance between any 2 points in our space. That's pretty safe. Then we can assign an anomaly score. I'll use A of x because this is no longer like a log probability. We just say an anomaly score is the distance to our kth nearest neighbor in the data set. And so the intuition here is if I'm very far away from all of you, over here in the corner by myself, my nearest person, actually my nearest, like, third nearest neighbor is maybe you. That's pretty far away. Whereas your third nearest neighbor is like right next to you, right? So you are not isolated. I'm all by myself out here. So this works pretty well. In fact, even in high dimensions, it works pretty well. Because basically, if you're a point alone in some empty region, then you're far away from your neighbors. And there are tons of refinements of this where we learn the distance metric and various other things. Another algorithm that we find is extremely cool and really is our winner in our benchmarking exercise is something called the isolation forest. So how many of you are familiar with decision tree classifiers? Yeah, so maybe a third. So the idea of a decision tree is basically a big nested if-then-else thing. So we're going to make a random if-then-else piece of code that'll have a tree structure. And so we grow it this way. We choose one of the attributes, one of the dimensions, one of the features at random, the jth one. And then we choose a threshold. So maybe we choose weight, and then we choose 20 kilograms. And then for each data point, if weight is above 20 kilograms, we branch to the left. Else we branch to the right. And we keep constructing basically this big random if-then-else structure. Until, and we can take our data, right, and drop it through the if-then-else structure until it reaches a leaf. And when each data point, in each leaf of this if-then-else structure contains only one data point, we say that that data point has become isolated. It's in its own leaf, separated from all the other data points. And the intuition is that anomalies should be things that are very easy to isolate at random. A very few number of random splits, and that data point is going to be separated from all the other data points. Whereas if we have a very tight cluster of points, we're going to have to do a lot of random splitting until we get each of those data points to be all by itself. So it'll be very deep down in the tree someplace. So we choose an attribute, we choose its threshold, and we choose the threshold randomly from the observed range of the jth value, between its minimum value and its maximum value. And so every data point is in its own leaf. And then let's let d of xi be the depth at which a point finally was isolated. So maybe a point got isolated right here, but maybe it didn't get isolated until it was way down here. So depth 1 versus depth 4, depth 8, depth 20. We create an ensemble of these trees. So we maybe build 100 of these trees, and we calculate the depth of each for a given query point. We drop it through follow it through the if-then-else structure, count how many tests it went through before it became reached a leaf, and that's its isolation depth. And so then we calculate the average of its isolation depths over all of the trees, and then we have a way of normalizing that to get a score between 0 and 1. And when I say we, I really mean these people, Liu, Ting, and Zhou. I didn't invent it at all. In fact, when I saw the paper come out, I thought, this is a stupid algorithm. Turns out to be the best one of all the ones we've looked at. So there's another interesting algorithm called LODA, Lightweight Online Detector of Anomalies. And what they do is, here's a cluster of data with a bunch of random outliers surrounding it. What they do is they generate random projections of the data. So what do I mean by a projection? Well, if I took all these data points and projected them onto the x-axis here, I would get some sort of probability density that looks like this. And this is a kernel density estimate along that x-axis. And so if I want to know the probability of this data point, I can look it up here, and it has a pretty high density on this projection. But I can generate another random projection. Maybe I randomly project onto a line that would slice through the space this way, and then I would get this kernel density estimate. And again, now this query point, when I ask how likely is it here, it's down here in one of the tails. So it has pretty low probability. And so suppose I do this 100 times and average all of those log likelihoods, then I get sort of the average surprise out of these random projections. And this isn't a true probability density estimator because we're really making a bunch of very low dimensional simple estimates, but it works quite well, and it's also very fast to compute. We say they are sparse random projections because, I mean, here it's only 2 dimensions, but if this was 1,000-dimensional data, we would choose maybe something like, what's the square root of 1,000? I should know this. Anyway, yeah. We choose a random, a square root of the dimensionality points, and and make only those non-zero when we're generating a projection vector. You generate a projection by defining a vector of weights and then multiplying each data point by that vector, and you get a one-dimensional quantity, taking the dot product. Okay. Well, we did a benchmarking study. So in the data mining community, probably the KDD conference. Is that a question? No. Okay. There have been many papers published on these kinds of algorithms, but they often evaluate on only a few data sets, or very easy ones, or proprietary ones that are not public. So we created a benchmarking data collection, and maybe I won't go through all the details here. But we ended up comparing 8 different algorithms on 2 different metrics, and we found that this isolation forest was really the best. Second best was creating multiple Gaussian mixture models and averaging them. The third best was a k-nearest neighbor type method called LOF. The fourth method was something called robust kernel density estimation, which is a way of extending kernel density estimators to higher dimensional spaces, and so on and so forth. Surprisingly, the 2 worst methods are ones that are very highly cited in the literature. One is called the one-class support vector machine, developed by a very, very smart group of people in Germany. But it turns out that, at least on these 2 metrics, which both relate to how well you can rank order, you want to rank all the anomalies higher than the normal points, they fail badly. And we don't really understand why.
So what was the sort of data sets you were?
So we were taking UC Irvine data sets. I don't have, I guess I have a list of them, but 19 data sets. So these were mostly classification and some regression data sets, and declaring some of the classes to be the anomalies and some to be the nominals. And then we were also doing systematic manipulations of various aspects, like what fraction of points are anomalies, how hard are they, how buried are they in the normals. We added irrelevant dimensions to see what the effect of that was, and we also tried to manipulate how clustered the anomalies were.
Yeah, I was thinking where the spatial data is kind of so different from, say, financial data maybe or something?
Yes. Well, and I don't have a plot in this thing, but the number one factor that determines the value of those metrics is the data set. So the choice of algorithm is actually the third most important thing. The second most important thing is how common are your anomalies. Because in this case, we're fitting our density estimators to data that contains anomalies. So we're fitting to contaminated data. And so if there's very little contamination, that's much better than if there's a lot. If there's a lot, then our fit is bad, and we think anomalies are normal, just like everything else. Yes. Well, yeah. And that takes us into the realm of robust statistics. Maybe I should stop here. I can go on talking for forever, but let me just skip ahead to the... I will tell one anecdote here, which is basically that we find that you don't need a lot of training data to fit these anomaly detectors well on these kind of database type data. You can't read the numbers here, but this is the amount of training data, and this is some measure of this is the area under the ROC curve, so how well it's classifying things. And what we typically see is that these are learning curves, and that the algorithms achieve pretty high performance after maybe only 1,000 data points. And so this is very different from e to the d over 2 kind of behavior that we would expect with kernel density estimates. And this is pretty consistent across a bunch of these different benchmarks. So we have a paper that tries to explain why that would be true. Okay, anyway, I will stop here. This is a very theoretical talk. When I get up here later in the morning, it will be much more about our weather data things. But I wanted to give a sort of tutorial on density estimation. So I'm happy to answer questions right now, and also I'll be here the whole time. So if you want to have a one-on-one tutorial, come and see me. But any questions right now for this? Or why don't you?
Why did you go for Regression? Why didn't you use any other distribution?
It was really, I guess, just a convenient choice. In the kernel density estimates, you mean? That's what you're asking?
What I mean, if you're given data, you never know its distribution.
Right, yes.
Now, for you just said you maybe
Well, that would be the right thing to do, yes, is to examine the data and, especially plot scatter plots and try to get an understanding of how Gaussian it is, how normal it is, how heavy are the tails, these kinds of things. Because if you have heavier tails, you could use a T distribution instead of a Gaussian distribution, and that because it has heavier tails. And there are other distributions with even heavier tails. The thing about a mixture model is you can use a bunch of Gaussians to sort of implement heavier tails, even though they're made out of lots of Gaussians. But it's true, Gaussians have these exponentially dropping tails, and so they often are not a good model of natural data, because weather is very non-Gaussian, for instance, as we'll discuss after lunch. Other questions? Yes, sir.
Sorry, I keep asking questions. The one thing I was wondering about, so you mentioned the second most important factor is the proportion of your
Yes.
data that's an anomaly.
Right.
It's kind of a bit vague, but when does it start going badly?
What's our breakdown point?
Sort of, I'm studying for the air pollution project, I need something like this. I worry that at the moment it's like 100% of the anomalies at the moment, so I need to work on that. But
Well, of course, the best thing is to take your data and try to clean it so that it doesn't have any anomalies in it, and then you don't have any worries. In a lot of the applications we've been doing have been in computer security, and fortunately, the actual anomalies are very rare, like maybe 1/100th of a percent or 1/1000th of a percent. And so the advantage is that your data are essentially clean. The disadvantage is when you actually go to set a threshold, you have a lot of false alarms because you're trying to find these needles in the haystack, these very rare events. And if the data naturally have rare events, then you're going to have a lot of alarms. So that's the downside. If the faults were more common, like maybe, I don't know, credit card transactions or I don't know what like M-Pesa does with, they probably have a fraud unit and probably are using some statistical tools there. And there you usually focus on the expensive cases. Who's costing us a lot of money? Because we have a fixed amount of investigator resources, we've got to go after and the same with cyber attacks. You want to find the ones that are really causing trouble, and maybe there's some you just can't afford to find them all. So.
I guess have you ever tried to just say with the weather thing?
Yes.
This is dangerous, I guess, but automatically just remove the outliers, as it were. But then I guess you end up biasing your data, so you never see extreme weather events, maybe, because you just try.
Right.
Is that like an area you've looked into?
Hold that question. We'll come back to that during the weather discussion. Yeah, that's a tough one. Yes, sir. Yes. Yes, the membership or the responsibilities.
The banana shape, the way you clustered that, how does it compare with the support to vector model? I mean, support to vector machine with the kernel T, as if it's telling.
There is a connection. Actually, the close connection is between kernel density estimation and support vector machine methods, because they both are kernel methods. And I don't know, I mean, I think you're going to learn about Gaussian processes later in this DSA? You were, yes? I don't know. Is Neil still on the list, or is he? I think Neil Lawrence will be here later in the week, and he will probably talk about kernel methods.
It's not me.
Yes. Yeah. So we can continue that discussion then, because that's also very closely related to what we're talking about here, using kernels. Yes, sir.
I would like to know what are the pros and cons of distance-based method, because I find them pretty simple and easy to understand.
The pro is that they work pretty well and they're easy to understand. The con is they basically take time that depends on the number of data sets. So when I get a query, I have to calculate my distance to every other data point. And so that's expensive. And to adjust parameters, I typically need to look at all pairwise distances among all data points, which is a quadratic calculation. But because it is such an intuitive algorithm, there's a whole set of very advanced tools for speeding up those distance calculations. So, we have the triangle inequality that says if when I know the distance to one point, I can use that as a bound on how far away I am from another point if I know its distance to that other point, right? And there's lots of cleverness has gone into this, and there are good packages that do it pretty quickly. So there's something called locality sensitive hashing that basically uses hash tables to do it really quickly. And so it can be done, but then the code starts being very simple, and pretty soon you have this incredibly complicated implementation. But other people have done it, so we can use that. Yeah, but it's a great question. Yeah, I think it's probably the very first thing to try in a new problem because it is so simple. Yeah. That and kernel density estimators are like the no-brainer methods. But they both suffer from this problem that you have to calculate your distances to the other data points. Yes?
So how does normalization play out in anomaly detection?
Normalization? It's not, I mean, if we're just trying to rank order our anomalies, then normalization is not important, really. It's just getting the rank order right. So that's a good question because we can avoid some of the headaches we get with normalization in other probabilistic applications because we only need to know the relative probability of two things. Yeah, but it's not a big deal. Yes?
Would you be able to use any of these methods to look at anomalous sequences?
Really, everything I've described here is just for IID data, but when we have sequential data, like in weather data, we have to deal with that somehow. So some people have been using, you can use time series type approaches, so autoregressive models or moving average type models, ARIMA models. There's also, of course, now neural network things, so using LSTM type models to model sequences is working well, and there have been several papers on anomaly detection in sequential data using those types of strategies. But it's pretty, it's not very mature yet. It's difficult, very difficult, I think.
Would the mass autoregressive
Could you extend it? I think you could, and there have been so many papers recently, I haven't read them all. I think there may be some attempts to do that with an LSTM type network to combine that with these regressive flow, these normalized flows to get densities out. We usually do things like, can we remove the trends from the data, sort of using traditional time series type methods. If you can, then you have a white noise process, and then you can apply these methods. Or you can, try various normalization tricks, and actually, in a lot of what I'll talk about with our weather data is the headaches that we've had with that, and how we're trying to deal with it. And our main strategy is to use two nearby weather stations that are experiencing the same trends, and just subtract them from each other, and then the trend disappears, and we can use these things. Okay, well, let's break here, I think. Yeah. Thank you very much.